So today we will start with a new topic, namely flow networks. To motivate ourselves, let's take a simple situation where we have a water source which supplies water, and there is a network of pipes. These are some junctions where more than two pipes meet. And so on. This is sort of a situation we want to deal with. This is a source and this is the sink. We want to transport water from here to here. And we have pipes of different capacities. So they can have various capacities, like maybe take an example. Maybe, well, this is better. Maybe this is 5, this is 15, this is 20, this is 3, this is 40. And we want to transport maximum water from S to T node. And the issue is how much water should be transported through various pipes, subject to, of course, their capacities. Now, normally, of course, in nature, water finds its pressure and decides where to divert itself, but we have to now compute in a discrete setup. So we will first define the flow network itself and give some other definitions necessary for the discussion. So let's start with the definition of a flow network, which is a tuple of set V of vertices or the nodes. The pipes will be now represented by directed edges. So we may have a little bit more general situation. We have a directed pipe, so pipe which can carry water in a specific direction. So we will assume that there is a connection between every pair of nodes, but not including, of course, loops. So we will remove so this denotes a complete graph, a directed graph, where there is an edge from each node to every other node. In addition to that, we have a function C. C is a function from edge set. So let us just call this E. To non-negative reals. And finally, we will have two special nodes S and T. These are elements of V. So this is the algebraic setup that we want to study. Now, this allows for having different capacities in edges between the same pair of vertices. So let us suppose this is x and this is y. I can have a capacity 10 here and 20 here. So this is how it slightly generalizes this picture. Now let us try to define the concept of flow. So flow is a function again, f is also a function from the edge set to non-negative reals, subject to the following conditions. So the conditions are that f of x comma y is minus f of y comma x. Well, after all, whatever flow is going from x to y directly, suppose some 8 units are flowing in this direction and 2 are flowing in this direction, then effectively it is as good as 6 flowing on this direction and 0 in this direction. So, we will, instead of associating this value to 0 and this to 6, we will have a slightly different notation. We will denote effectively the net flow. So, this says if x to y is 6, then it simply says that y to x is minus 6. Another important condition is that the flow can never exceed the capacity of the edge or the pipe. So, we have a bound of C x comma y, the edge x comma y has capacity C x y. This has to be an upper bound for the flow from x to y. So, you can never send a flow more than 10 units from here to here, or you can never send more than 20 units from y to x. And because of this condition, this is also implied that this is greater than or equal to minus y comma x. Because this is equal to minus f y x. The third condition is, let us just again look at this diagram. These two are special nodes. This supplies water and this one consumes it. But apart from these two nodes, if you look at the other nodes, there the total flow must remain conserved. Whatever comes in is what should go out. We always talk about stationary state picture. So, this we have to capture, that there is no net flow coming from any node or net flow consumed by a node. So, we will add this condition, namely sum f x comma y, remember f x x is 0 always. So, this is the net flow coming out of node x, should be 0, and similarly the net flow going into x should be 0. This is true for all x in V minus s comma t, that is apart from these two. We also insist that source is the one that supplies. So, f of s comma y should be greater than or equal to 0 for all y, and f of y comma t should be greater than or equal to 0 for all y. So, these are the conditions for a valid flow in the network. Now, there is a notion of residual capacity. So, suppose you have an edge with capacity 10 and there is some 7 unit of flow going in this direction. There is an edge between the same pair of nodes with capacity 20. So, of course, 0 is going in this direction. So, if you notice, we have capacity to add 3 units of flow on top of it in the direction from x to y. So, subject to the given flow, the residual capacity from x to y is 3. How about the residual capacity from y to x. So, well, obviously, we can put 20 units of flow in this direction, but whatever 7 units of flow is flowing in this direction can also be neutralized. So, that can also be added in this direction, and in all there is a residual capacity of 27 units from y to x. So, we define residual capacity as C subject to a given flow f from x to y as C of x to y minus f of x to y. So, that defines a residual capacity which will be useful later on. If C f x y is 0, then edge x y is said to be saturated. So, no further flow is possible in the given direction x to y. Now, one notation which comes in handy, I want to define. So, let u and w be subsets of the vertex set V, and indeed u and w may overlap, they are not necessarily disjoint. Then f u comma w denotes the sum total of the flow f x comma y, where let us write down two sums, x belongs to u and y belongs to w. So, this is just a compact notation for this sum. So, now let us try to give a graph based representation of a flow network and a flow in it. So, let us say we have following network with this node, source node S, sink node T, and maybe there are few nodes here. There are of course edges in both direction. So, let us just complete this first. Except on these nodes, there are no incoming edges into S because of our condition that all the flow through S will be always emerging out of S. Similarly, here every edge is actually converging into the sink. All other edges are in both direction. So, one can think of such a notation. Now, of course, this is a complete graph. So, there are edges of between all pairs of nodes. So, maybe I will add these edges, and there is of course here as well, and so on. So, if it is not complete, just add that, because you will also have edges here and you will have edges from S to T directly. but look at it, this looks pretty dirty, not very useful way to represent it. So, what we will do is, we will, if I have to show a flow, I will only show those edges on which there is flow, and if the flow is empty, I will withdraw those edges. So, let us just simplify and imagine a simple picture. So, let us suppose you have only flows, maybe there was an edge here, a vertex here, and let us suppose there is a flow over here into this as well, and there is a flow going in there, one going there, over here, here and here. So, we normally show the capacities on the edges like that. And we will show the flow, actual flow passing through it. So, maybe it looks like this, and maybe 10 out of 50, 4 out of 4, etc. I just want to construct one example of a valid flow. So, I will just concoct some numbers. Here I am showing 10 units passing into this, 10 going from here to here. So, this seems to be conserving the flow. 4 units coming here, say 2 going into this, 2 going into this. 17 is coming in here, maybe there is an edge over here. 10 going through this, 7 going into this, and so on, maybe 12 here. So, I hope this is correct, but in case it is not, one has to just check. But anyway, the whole purpose is that one can actually represent a particular flow in a network like this by just removing those edges which are currently not being used by the flow. So, now let us define a notion of a cut. Cut of a flow network. Now, take a small example. Very simple example, S, T, A and B. So, the cut is actually partitioning of the vertices into two subsets such that S belongs to one of the subsets and T to the other. So, we define a cut C as tuple S comma V minus S. So, this is say S side and this is V minus S, such that S belongs to S and T does not belong to S. Then we define the notion of the capacity of the, or rather first of all let us talk about the edge set. The edge set of a cut E of a cut S comma V minus S. Okay, this is the set of all the edges x comma y such that x belongs to S and y belongs to V minus S. So, we are here representing those edges which are pointing from a vertex on S side towards a vertex on the complementary subset, and capacity of a cut S comma V minus S is the cumulative capacity of these edges. So, we will add up C x comma y, x in S, y not in S. So, this is the total the sum of the capacities of the edges crossing this. So, here we will consider this edge, we will not consider this edge in the wrong direction, this edge and this edge. These three edges constitute the edge set and their capacity sum is the capacity of the cut. So, now here I am going to claim a very simple fact, but useful. So, the claim is that an edge set E prime of the complete edge set E is the edge set of a cut if and only if the following, that every path starting at, remember this is a directed graph, so paths are all directed, every directed path from S to T passes through at least one edge of E prime, and E prime is a minimal set with this property, if and only if E prime is a minimal set with the property that every path which is directed from S to T passes through at least one edge of E prime. Okay. So, this right hand side is actually a characterization of the edges of a cut or the edge set of a cut. What this is saying is that every path passes through at least one edge of E prime, and this property breaks down if I withdraw even one edge of E prime from the collection. Then in that sense it is minimal. So, let us try to prove this claim. First of all, let us say we are given that E prime is the edge set of a cut, some cut. Well, to see that every path should pass through at least one edge of E prime, let us take some arbitrary path from S to T. Consider a path S V1, V2, Vk, T. So, there is an edge, of course, S to V1, V1 to V2, and this is a complete graph, so there are edges, and it starts at S, ends at T. This belongs to S, this belongs to V minus S. So, as we proceed from left, there has to be some first vertex which belongs to V minus S. So, let us suppose that vertex is Vi plus 1, which means that up to Vi all the vertices are in S, and here the first vertex occurs which belongs to V minus S. Well, obviously Vi plus 1 could be T. So, there is no problem about existence of this. Well, hence Vi belongs to S, and the edge Vi plus 1, if Vi plus 1 is the first vertex from left, that belongs to V minus S, then now note that Vi plus 1 cannot be S, so there is always a vertex before it. So that is why I am just writing this as Vi plus 1. Well, in that case Vi belongs to S and edge Vi plus 1 belongs to the edge set of S comma V minus S. So we have established that no matter what path you give me, there is always at least one edge in the path belonging to this set. Now to prove that this is a minimal such set, so to prove minimality, let me take off an edge. So consider E prime double prime equal to E prime minus a some edge x comma y. Clearly this is in S and this is outside S. So this is one edge we have taken off. Now I can actually form a path, namely T x y, sorry my mistake, S comma x S x y t. Consider this simple path of three edges as S and x both belong to S and these two belong to V minus S. This edge does not belong to the edge set of the cut. This edge does not belong to the edge set of the cut, and now x y also does not belong to the set E double prime. So E double prime fails to have that property that we have described here. Hence, E prime is a minimal set having the property that every ST path passes through it. So this is the one side of the story. Let us prove the converse. Let us suppose there is a set, suppose there is a set which has this property and it is minimal. Okay. So let E prime has the said property and it is minimal with respect to the this property, with respect to this property. So we want to prove that this has to be equal to the edge set of some cut. Alright, so let us define a set S. We define S to be those vertices which are such that X is reachable from S, small s, without passing through E prime edges. What it says is, consider paths from S which do not pass through any edge E prime, any edge of E prime. Wherever it can reach, those vertices are put in S, which alternatively means there is a path from S to X without any E prime edge on it. All such vertices are collectively put into S prime. Now consider the cut S V minus S. We will prove now that the edge set of the cut is contained in E prime. So let us define this subclaim that E S comma V minus S is contained in E prime. Okay. So to prove this, we go by assuming the contrary and prove an absurdity. So assume contrary, let edge x y belong to E S comma V minus S, but does not belong to E prime. Okay. It does not belong to E prime, but it belongs to the edge set. So, by the definition of this edge set, x belongs to S and y belongs to V minus S. This is the definition. Okay. Now, so there has to be a path from S to X, because by definition S is the set of vertices reachable from S through directed paths without passing any edge of E prime. So we must have had a path S to vertex X. Now that we have also assumed that this edge x y does not belong to E prime, so that path can be extended to y, because this also does not belong to E prime and this is one of those valid paths. So this implies that y belongs to S as well, because y is also reachable from S without passing through any edge of E prime. But what we notice here is that y belongs to V minus S, which is a contradiction. So we conclude that this set must be empty. In other words, E prime contains every edge of the cut set of edge. So let us just write down this complete argument. Now since x belongs to S, there is a path from S to X without passing through E prime edges. Now since x y does not belong to E prime, this path can be extended to y. Hence, by definition of S prime S, y also belongs to S, but as given here y belongs to V minus S. So this is a contradiction. So we have seen that every edge of the cut belongs to E prime. But there is another assumption, namely that E prime is a minimal set with this property. We have already shown that the edge set of every cut has this property, which means that property is satisfied by E as well. So, if E prime is strictly larger than this set, then this cannot be a minimal set with the property. So, finally, we can say, since E of S comma V minus S has the property, what property I am talking about? I am saying the property that every path from S to T passes through the given set has the property, and E prime is a minimal set with the property. Hence, E prime better be equal to, so they better be equal. So, now let us talk about one more interesting fact about the networks. So, the second result that I want to state needs this definition. Definition of net flow So, given a flow as we have defined is a function which gives values associated with edges, say f, net flow of the function f, we denote that by modulo f. This actually defines the total amount of fluid that enters into the network. So, this can be stated as f s comma y, where y belongs to v. Okay. This is the total quantity of fluid that emerges from the source and enters into the network. And in our notation that we had defined earlier, this is same as f s comma v. So, here is a claim . So, this says that for any cut the capacity of the cut is greater than equal to f s comma v minus s, which is equal to the net flow as defined here. What this says is that the total capacity of the edges jumping from S to V minus S side is always greater than equal to this quantity, which actually is nothing but the net flow passing from this set to this set of nodes, the net flow. So, let us try to prove this. F s comma v minus s. This we can express as from the definition f x comma y, x belonging to S and y to V minus S. This was the definition. And from the one of the conditions, namely that the flow can never exceed the capacity, we can bound this and say that each value f x y is bounded above by C x y, where x belongs to S and y to V minus S. This is precisely C of S comma V minus S. That is this inequality. So, now let us try to show that these two are equal. Okay. Consider f of S comma V. F S comma V is f of S comma S plus f of S comma V minus S. If you just expand this, you split that sum into two parts, you get f S comma S plus f of S V minus S. Okay. So, now the question is, what is this expression? F of S comma S, let us just look at it. F of S comma S is some f of x y, where x and y both belong to the side S. So, this is actually 0. The reason is, for every pair x y, we also have pair y x, and their value is equal and opposite. So, they cancel out each other, and this term reduces to 0. So, the f S V is same as f S V minus E, V minus S. Now, let us expand f S comma V, and that is some f x comma y, x belonging to S and y which runs over entire set V. So, let us split this into two sums. One is f S comma y, y in V, plus summation x belonging to S minus small s, f x comma y, y belongs to entire set V. Or maybe I will write down just slightly differently, y belongs to the whole set V, where x goes to runs over S minus S, small s. This is the same expression as this. So, let us just take a look at this sum. Note that this x is neither equal to S nor equal to T, because T belongs to the complementary set of S. Hence, the conservation law says that this is equal to 0. So, this second term vanishes, and the first term is by definition the net flow. Remember, that is how we have defined it. So, this is nothing but net flow. So, this we have shown is equal to mod of f. Hence, the net flow is equal to this. That is the second equality. What does that mean? So, let us take a look at a simple picture. I have suppose we cut the network here. This result states that whatever flow that has emerged out of the source is exactly equal to the net flow passing from side S to side V minus S in this direction, and that is precisely what we should have due to the conservation rules. Hence, as a corollary, the net flow should also be equal to F V minus T and T. This is a special cut, namely this cut. This is also equal to sum F x comma T, or x belongs to V minus T, which is the net flow going into the sink T, which is again as expected, whatever emerges from here eventually enters into the sink. Okay. So, now we have more or less defined all the basics, and towards the end I want to define a problem. So, let us just imagine a situation where you have a mining company M which has a site somewhere, there is a steel mill somewhere quite far off, and there are several towns in between. Assume that mining company can generate enough coal and steel mill is also ready to consume as much as is available. We have some transport companies which provide connectivity, which can carry coal between towns. So, maybe this is how it looks like. And so on. Our objective, okay, one more thing about these transport companies is that they have certain limited capacity. In a given unit time, they can carry at most so much coal. So, they have been, there is some capacity C1, C2, C3, C4, etc. associated with each of these lags in the transportation. We want to compute what is the maximum coal that can be transported from M to S and how. So, we would like to know what is the maximum amount that can be transported and which edge must carry how much, so that we can realize that maximum flow. And that is precisely the problem that we want to address next in the next lecture, that is to compute max flow in a given network. Before I close, the last point is about multiple sources and sinks. Suppose we have several sources as well as several sinks in the network. How does this problem change in that case, or how do we handle this? And the answer is actually very, very simple. So, what we do is we define two artificial nodes. So, these are new source and sink nodes, and these are reduced to regular ordinary nodes. So, they have whatever edges we have. On top of it, we add the new edges in the direction from new source to the original sources, and from original sinks to the new sink, and associate infinite capacities to each of these edges. Now, this becomes a regular one source one sink problem, and the thing that I want to argue now is that every solution of this is a solution of the original problem, and every original problem solution is essentially a solution of this, and the reason is the following. Suppose we are given a solution of the original problem that would generate certain flow out of each of these sources. So, let us call them S1, S2, S3. Whatever the flow emerges out of it, let us say some alpha 1. So, we can send alpha 1 flow from this, alpha 2 from this, alpha 3 from this. Similarly, whatever is sinking into this, namely beta, we will send that beta 1 into this, beta 2 into this, and so on to this. So, that becomes a valid flow of the extended or enhanced flow network, because now the net flow here is 0. Similarly, net flow here is also 0. So, every solution of the original problem is a solution of this, but the converse is also true. If you once you solve it, you remove this portion completely, and now you have got a solution of the multi-source, multi-sink problem. Hence, one has to compute only a max flow solution for this enhanced problem, and from that we will get the max flow solution of the multi-source, multi-sink problem. We will continue with more of this in the next lecture.